In this segment, we'll continue our look at margin vector, discussing derived class constructors, like that one there, and we'll also do a deep discussion of static methods and members. Now, subclass constructors require special design, especially in the presence of private members in the superclass. The subclass constructor is responsible for initializing all of its class members, including those inherited from the superclass. But if superclass members are private, it cannot do this directly. Also, all the logic for setting up superclass members is already available in the superclass constructor or constructors. So the right solution is for the subclass constructor to call a superclass constructor, passing any necessary parameters in order to get the superclass data correctly initialized. And you might think this would be done via code like a call of, say, vector on x and y, or init x and init y here in this call. But in fact, the Java syntax instead is as shown right here. It's a call to super, and then you pass the parameters init x and init y. And this calls the two-parameter vector constructor, superclass constructor, passing initial values for x and y to it. Now, if there are any members to initialize that were added by the subclass, then their initialization goes directly in the subclass constructor. Though for margin vector, there are none needed. We don't have any instance member data that were added by margin vector. So in summary, a subclass constructor should always initialize superclass members by calling, via super, a superclass constructor, passing along any relevant parameters. And after that call, the subclass constructor then takes care of any initialization of subclass members. So what happens if you don't call super? It's not an error per se. The compiler will let you get away with it if the superclass has a default constructor, like vector does. Right here, bringing it up temporarily in Eclipse. In this case, you get an automatic call of super default, invoking the superclass default constructor with no parameters passed. But that's often not what you wanted, so it's better to always make an explicit supercall. Now there is one sometimes useful exception. If you have a simple subclass that has no data members of its own, or is content to let Java's default initialization take care of them, and if the superclass has a default constructor to take care of its data, then the subclass can dispense entirely with constructors and have none. The superclass default constructor gets automatically called. Now, in an earlier segment, I promised a closer look at static members, like these here. In vector, we had a final static member, but margin vector has our first example of a modifiable static member, margin. Our design presumes that all margin vector objects will use the same margin of tolerance, so there's no point in having an instance member, a non-static member, to hold that value, repeated in every margin vector. A single static member, or recall class member, synonymous term, shared among all of the margin vector objects will suffice. But it's more than just a matter of saving space. We can also set or change margin for all margin vector objects at once without needing to change it for each individual object. If margin were public, for instance, then we could simply write margin vector.margin equals 3.0, something like that. The name margin alone, by the way, is insufficient, since there may be other variables, locals, or members of other classes with that name. To be clear that we mean the static margin member of margin vector, we add class scope, the margin vector dot, and that clarifies it. Now, it's important to understand that that's not a method call on an object called margin vector. There is no such object, and margin vector is a class name. It's not a reference. When the dot operator is preceded by a class name, as in this case, then it indicates that we're referring to a member of that class. Some languages use a distinct operator for class scope. C++ uses double colon, for instance. For a normal method call, the type of the context object makes the class implicitly clear. But accessing static members or methods outside of the class or of one of its subclasses requires this class scope. But of course, margin is private, so this assignment here won't work anyway. Instead, margin vector does supply static setMargin and getMargin methods to modify the private margin member. An example call of setMargin is actually down here in vector test, margin vector.setMargin 3.0. Now, let me ask a quick question about that call. What is the context object for the call? Indeed, at that point, how many margin vector objects even exist at the point the call is made? And is that a problem? Why or why not? After a pause, first of all, it's a static method, right? It doesn't have a context object. And in fact, there are no vector or margin vector objects at this point in the code. None of them have been created yet. But this isn't a problem because, well, setMargin doesn't need a context object. Static data and methods exist independently of any object of the class, and they exist even if there are no objects of the class. Indeed, there are some classes that are entirely comprised of static methods and members and have no instance methods or members at all. You never create objects of such classes, you just refer to the static members or methods with class scope. In effect, the class is simply a way of grouping a bunch of related methods together, somewhat like a package. In question 2, we used such a statics-only class, in fact, in the code for vector. Where was that? I'm returning from a pause and bringing up Eclipse here. Well, it's down here where we used math.square-root. The methods like math square root, math sine, etc. are all static, and they're called with math class scope. The math functions don't need a context object since they simply operate on their parameters. We never write new math or use a math object. Indeed, we can't because the math constructor is private, which is a common design trick for preventing unwanted creation of objects by code outside of the class. Question 3 then. What if I wanted to write a static method to set all the x values in all margin vectors? Would this work? I write, for instance, public static void set all x's and pass a new x value that I want to have, and then set x to that x value. Think carefully on this, with special attention to what the compiler will want to do with that x reference right there. Review the prior discussion on context objects if needed. Okay, returning from a pause there. And no, it won't work. The reference to instance member x is implicitly translated, of course, to this dot x. And there is, once again, no static, context object in a static method. It has no this. So static methods can refer to static members. setMargin, for instance, can obviously work with margin. But they cannot refer to instance members, because doing so invites the question, which object's instance member did you mean? And a static method has no context object with which to answer that question. Note, though, that the reverse is not a problem. An instance method may refer to a static member, as we do in equals, for instance, referring to margin. And in that case, the context object is simply not used, and the instance method refers automatically to the one shared copy of the static member. So, question 4. Are we saying then that a static method can't access non-static members, period? What if I do something like this? And this is so big, I'm going to let you read it in the code, or in the transcript, if you would, please, instead of trying to drop it in the diagram. I'm going to declare a funny method. It's static, and it declares a margin vector as a local variable, a new margin vector referenced by MV, and then modifies MV's x data and changes it to 3.0, and x, of course, is, again, an instance member. So will the reference to mv.x be rejected? Make your best call based on the reasoning we've just done about context objects. And returning from a pause, yeah, that will work, actually, though it's a bit unusual. There is an object, mv, for the reference to x, even though funny method has no context object itself. Static methods are not pariahs. They're welcome to access instance members, but they need to get an object first, and they need to specify it when accessing the instance members. So let's summarize all this to get a good set of rules for static methods, and I'll just stick the transcript right in the diagram here. Static data members. 1. They're shared among all objects of the class, and they can form a sort of blackboard to which all objects may refer. 2. They exist even if there are no objects of the class. And 3. They can be accessed by static or non-static methods of the class. Static methods. They have no context object. They're not associated with any particular object of the class. They must be called with class scope if they're called from outside the class or its subclasses. And they may be called even if there are no objects of the class. And finally, they can access static members, but they cannot access non-static or instance members unless they can fish up an object with which to do so, like we did with the MV example. Now, many older languages, for instance C, offer global variables that exist independently throughout the program's life, and also offer global scope functions that are callable from anywhere. Static members and methods are the closest that a modern language like Java gets to this. Static member data are like global variables, but they're limited to the class they belong to, and thus they're not as dangerously modifiable as true globals. Recall the bullseye on the forehead metaphor in an earlier lecture. Static methods are like global scope functions in that, if public, they can be called anywhere without an object. But they have citizenship in a class, and they're scoped to that class, and they have special access within the class. In the next segment, we'll review the two most important concepts in object-oriented design, which we've been leading up to: the ISA relationship and method polymorphism.